Hello, this is my English speaking practice, and I'm talking about my tech study. And today, what I'm going to learn, I haven't decided yet. I have three options: system design, operating system, or technology for game or game development. But today I feel like coding. So I wanna design the how to implement these features. But it's not. No, it's not today. Because I haven't developed the game core logic, so I'm gonna implement these features. So lately, so I will implement these features later on, at a later stage. Later. Okay. So I choose this system design roadmap. For example, yeah, there are a lot of topics. And from today, I also focus on my English expressions because I want to improve my English skills. So it's not good to just to speak English as coming to my mind. I will use ChatGPT to know the correct expressions. Okay. And today, what topics I should learn? But I feel like I'm not. I have less motivation. In order to speak something in English, I started this stream, but I have no plan and I have less motivation. So what to do? what to do. Hmm. What to do? Hmm. Performance and scalability. A service is scalable if it results in increased performance in a manner proportional to resource added. Generally, increasing performance means serving more units of work, but it can also be to handle larger units of work, such as when data set growth. Another way to look at performance versus scalability. If you have a performance problem, your system is slow for a single user. If you have a scalable problem, your system is fast for a single user but slow under heavy load. Okay. Let me read this sentence, but it's PDF, slide share. Scalability, availability, and stability parents. Type safe. I've heard of type safe. Type safe Inc. renamed to Lightbend. Martin Odaski. He's a creator of Scala programming languages. Okay. Oh. Okay, CTO type safe. Scalability parents, managing overload. Scale up and scale out. Recommendations. Referential transparency. Laziness. Think about your data. So this is about coding style, programming style, and stuff. Scalability trade-off. Well, this is a general recommendations. Scalability trade-offs. Almost scalability. This is about all of system designs. It talks about scalability, availability, and stability. So almost all of system designs. I want to. Oh, okay. Today I have a topic to learn. Uh, I have a topic to learn today, and that is I/O multiplexing. And I've heard that I/O multiplexing is used for performance in single-threaded environment. That's a good starting point. Let me polish what you said into more mature English and then give you a short explanation of I/O multiplexing. Today I want to learn about I/O multiplexing. I've heard that it's used to improve performance in single-threaded environments. I've heard that I/O multiplexing is used for performance. Is used to improve performance in single-threaded environments. Multiplexing is a technique that allows a single thread to manage many I/O streams, like sockets, files, or pipes at the same time. Instead of blocking on one I/O operation, waiting for data from one socket, the thread can wait for multiple events and handle whichever becomes ready first. Common system calls for I/O multiplexing are select for equal KQ. This is especially useful for network servers like chat servers or proxies that need to handle thousands of connections at once without spoiling thousands of threads. So your understanding is correct. I/O multiplexing is about efficiency in a single-threaded environment because it avoids idle waiting and context switch overhead. Would you like me to also give you a short code example? No, I know these kinds of system calls. So this is okay. I understand. This is almost about asynchronous I/O or non-blocking I/O or like that. So the process don't need to wait for I/O because when the non-blocking mode the read or write system calls returns immediately with specific errors. That is a non-blocking I/O. Yeah, and after that, the process use this system call to observe the socket or files or pipes. Yeah, and if these files get available to read or write, the event happens and the process can detect and resume its process. So I/O multiplexing is using that mechanics. Yeah, this is my understanding. Okay, I understand that. So it uses non-blocking I/O, right? And it combines or it uses a lot of non-blocking I/O. That is a mechanism, right? And right now I have a new question. What is the difference between non-blocking I/O and asynchronous I/O? I feel like that is same, but there is they are different words. So I just curious. Non-blocking I/O calls returns immediately even if the operation is not finished. Yeah. May return right away with data no data available. Then you need to check again later, pulling or combine it with I/O multiplexing to know when the data is ready. Asynchronous I/O. With asynchronous I/O, you submit a request, and the kernel completes the operation in the background. When it's done, it notifies you. You don't have to keep checking if it's ready. The kernel handles the operation asynchronously and tells you when it's finished. You can continue doing other work at the meantime. Analogy: you go to a restaurant and ask if the food is ready. If not, you say not yet. They say not yet. You keep coming back to check. You order food and the restaurant calls your phone when it's ready. You don't need to keep checking. Non-blocking I/O multiplexing is used in event loops like Node.js and Nginx. Asynchronous I/O is harder to implement well, but modern Linux has things like I/O uring for efficient async I/O. So the difference is you check when it's ready. The system tells you when it's ready. Would you like me to also show you a small comparison in C code? Yeah. Non-blocking. This is easy. I understand it. I already understand it. So create a socket and make socket non-blocking, and here it connects with socket and create ePOL instance. This is for observing for socket. So this is ePOL file descriptor, stands for ePOL file descriptor. And here it register or subscribe or like that. So subscribe the event of ePOL in this file descriptor. The socket is here and file descriptor is here, and it needs to wait for events like this. So in this case, the process will stop here until the data comes. So ePOL wait and file descriptor and event is here. And if it returns a data, it means the data is available, so the process resumes. And since there is available data, so we can use the read function for socket and read the data to buffer, right? Like this. Okay, so we keep checking like this. An asynchronous IO with IOU ordering. Maybe this is also system call, and this is newer than ePOL. I think here we submit a read request and get notified when it completes. Maybe what is this? A ring, IOU ring, and struct U ring Q init. An open file, read only. So the file descriptor describes this file, and prepare a read request. Prepare read. I have no idea about this line, but IOU ring sequence CSQEFD buff. Submit request. Wait for completion. SQE, CQE. This is my mistakes. This function, maybe don't wait. It needs to run loop, and maybe if there is no events, I don't know. Would you try to help me? Timeline diagram. Yeah. I didn't understand. I haven't understood yet. This is non-blocking. Connect. ePOL wait. Not ready. Ready now. Read. Date. And asynchronous, just submit read to kernel. The kernel reads in background. I see. So the difference is you need to read explicitly like this, but IOU link, they integrate reading the data so it can take the buffer as arguments. So evaluate. evaluate itself is blocking. Ah, I see. Huh? Okay, so the read here is non-blocking because socket is non-blocking, so maybe this function returns equal or less than 0. And reach here again, evaluate. Does not return immediately by default. It blocks until an event occurs. Wait for IO event. System call waits for event and evolve. on the ePOR instance referred to by file descriptor EPFD. The buffer pointed to by events is used to return information from the ready list of file descriptors in the interest list that have some events available. A server-style continuous loop that real-world application use. I see. If no file descriptors are ready, wait will block. Yeah, this is my understanding. Yeah, until at least one FD becomes ready, unless you specify a time out of 0. Yeah. I see. And maybe so the model is not different. Because it doesn't need to call read explicitly. Conceptually similar to ePOR wait, in that both wait in kernel until something happens, both returns an event when the kernel has something for you. Two key differences: who does the IO operation? Yeah, you still need to call read or write. Returns a completion of IO. you already submit an async read and the kernel completed in the background, so when waitcque returns, you already have the results, no need to call us. Yes, this is good. Abstraction level. EPOL is an I/O readiness notification system, submission and completion system. That makes sense. Okay, that's it. I'm already tired, so it's time to finish. Thank you for watching.